So the siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. So we have the frequency of a source being 680 Hz. And then a man is standing with a detector that records the wavelength of the sound emitted by the siren, as shown in the diagram below. And yeah, there you have it on the left hand side. And then it goes on to say the speed of sound in air is 340 meters per second. So we have our V being equals to 340 meters per second. And then 6.1 says calculate the wavelength of the detected sound. This is quite an easy one because we all know that the frequency is equals to the speed in the medium divided by the wavelength, right? We are given the frequency of the emitted sound, and it's said to be 680 Hz. And then the speed of sound in air is 340 meters per second, right? So we have 340 divided by what we're interested in, the wavelength. From here, you just cross multiply and we get our wavelength. So we're going to have wavelength is equals to 340 divided by 680 Hertz. And then 340 divided by 680, that is 0.5 meters. So the wavelength of our detected sound is 0.5 meters. And then we have 6.2, which starts by a statement. It says the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of the sound of the sound, which differs from the previous reading by 0.05 meters. Okay, so we have a change in wavelength which is equal to 0.05 meters. Okay, before we go any further, it is said that the ambulance is moving towards the man, right? So from here, we should know that the new wavelength of the detected sound will be equals to 0.5 minus 0.05, which is 0.45 meters. Up to so far, there's no question that is asking us to do this, but then it's just obvious because I'm reading the statement and I understand what it is saying. So I know that the new wavelength that is going to be detected is going to be 0.45 meters. And then 6.2 says state the Doppler effect. That's just a definition. I don't expect anybody to get that wrong. It says the change in frequency, pitch, or wavelength of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. This definition is just basically the formula, really. It's the change in frequency, pitch, or wavelength of the sound detected by a listener because the sound source and the listener have different velocity relative to the medium of sound propagation. And then we have 6.3. So 6.2, that's the definition. And then 6.3, it says, how will each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? And then we have 6.3.1. It says distance between the wave fronts. The distance between the wave fronts is directly proportional to the wavelength. And if you can see here, I've already shown you that the wavelength will go down when the sound source is moving towards the listener. So for 6.3.1, we'll have decreased, right? Because the options we have is increased, decreased, or no change. So we're gonna have decreased because the wavelength will go down, so that means that the distance between the wavefronts decreased. And then we move forward to 6.3.2, and then how will the frequency of the detected waves change? Okay, the frequency is equals to the speed divided by the wavelength, right? So frequency is inversely proportional to wavelength. The wavelength went down, so the frequency goes up, right? So we're gonna have increased. And then 6.4 says calculate the speed of the ambulance, right? So in Doppler effect, there's really 2-3 formulas you can use. You can have the frequency equals to the speed divided by the wavelength, and then another formula you can use is always frequency of listener equals to V plus or minus the velocity of the listener divided by V plus or minus V plus or minus the velocity of the source multiplied by the frequency emitted by the source, right? And then this question says the speed of the ambulance. This formula cannot help us with the speed of the ambulance, so this is the formula we're going to use, right? So now we have to identify all the information we have and then decide on how we can determine the speed of the ambulance. So the ambulance is the source, right? So we are interested in this VS here. We are interested in this VS. We have V because V is the speed of sound in air, and then frequency of source, we have determined it. Oh no, we didn't determine it. It is given to us as 680 Hz. And then frequency of listener, we can determine it because we now have the wavelength when the ambulance is moving towards, right? Which we determined to be 0.45 meters. So we're gonna have frequency of listener equals to 340 divided by 0.45, and then that will be in the units of hertz. So let's leave it like that. Let's not solve it any further. We're just gonna keep it like that. So now we have frequency of listener equals to this is the speed of sound in air, and then the sound, the listener is stationary. So we're gonna have plus or minus 0, right? And then divided by the speed of sound in air again, V, and then the source is moving towards. When the source is moving towards, we get a minus in the denominator. So we're gonna get minus the velocity of the source multiplied by the frequency emitted by the source. If you don't know how this formula comes about and why I'm choosing minus on the denominator, then watch my introductory video that I'm gonna link on the top left corner. And then the frequency of listener, we say that is 340 divided by 0.45, and then V is 340, then plus or minus 0, we don't have to put anything there. So we have 340 again minus velocity of source multiplied by 680 Hertz. Now when you add this step, it's just a matter of how you want to solve it, the mathematics, right? It's you're almost done with the physics here. So the way I'm going to solve it, I'm going to divide both sides by 680, right? So I'm going to have 340 divided by 0.45, and then everything divided by 680, right? And then if I divide by 680 on the right hand side, that 680 is gonna get cancelled out. So now we're gonna have 340 divided by 340 minus velocity of source. I'll go ahead and cross multiply. I'll get 340 divided by 0.45 multiplied by 340, right? And then minus 340 divided by 0.4545 multiplied by velocity of source, which is equals to 680 multiplied by 340. So I can take this expression here to the right hand side. I'm gonna get minus 340 divided by 0.45 multiplied by velocity of source equals to 680 multiplied by 340 minus our expression, right? So let me just try copy it and paste, right? So minus this expression here, right? So after that, I'm gonna divide both sides by minus 340 divided by 0.45, right? So that I can isolate Vs. So I'm gonna get Vs equals to, let me copy this expression here. So I'm gonna copy that expression and then I'm gonna duplicate it. So now I have Vs equals to this expression divided by minus 340 divided by 0.45. And now I can put this entire expression here in the calculator and determine Vs. The reason why I don't want to press the calculator before I get to the answer is because I'm avoiding making mistakes, right? I rather put things in the calculator once and get the answer rather than put things in the calculator a lot of times and risk making a mistake, right? So I'm putting it on my calculator right now. So divided by minus 340 divided by 0.45, and that is exactly 34. Oh, 34. Why am I writing 340? Exactly 34 meters per second. If you have divided along the way, you've multiplied and you put it in the calculator, you're probably gonna get 33, something or 34, something. But then if you just solve it without putting it in the calculator and you only press the calculator at the end, you're most likely to get the most accurate answer. So I have a question here that I was doing with my learners during the day, and I just thought I should share it with you guys. So we have a sound source that is moving in an easterly direction towards the stationary learner at 15 meters per second. The frequency observed by the learner is F1. So when this sound source, right? Let me just write that down. So we have sound source. When it's moving towards the east, it's moving with a velocity of 15 meters per second towards the learner, right? The listener. And the frequency observed by the listener, it is said to be F1. And then it goes on to say when the source is stationary and the learner moves in a westerly direction. So now we have a learner moving towards the west, and then the learner is moving towards the source at 25 meters per second, right? So we have velocity of observer being 25 meters per second. The frequency observed by the learner is F2. So we have frequency observed, which is F2. It goes on to say that F2 is greater than F1 by 37 Hertz, right? So we're gonna get F2 equals to F1 plus 37 Hertz. And then 6.1 says write down the name of the phenomenon that the learner observes and state this phenomenon in words. So we know that the phenomenon is Doppler effect, right? Because the observed frequency and the emitted frequency are different because of the relative movement between the sound source, the listener, and the speed of sound in air. And then 6.2 says, assuming that the speed of the sound in air is 340 meters per second, calculate the frequency of the source. So let's start with our scenario 1, right? This is our scenario 1, where the sound source is moving towards the listener with a velocity of 15 meters per second. So we know fully well that frequency observed is equals to the frequency emitted multiplied by v plus or minus the velocity of the listener divided by v plus or minus the velocity of the source, right? And then the frequency observed by the listener when the sound source is moving towards the listener, we are told that is f1, right? So we're going to substitute f1. And then this is equals to fs because we don't know what the emitted frequency is, right? And then the speed of sound in air is 340. And then it is said that the listener is stationary when the sound source is moving towards the listener, right? So we're going to have plus or minus 0 here. And then divided by 340 minus Vs, which is 15, right? Because the sound source is moving towards the listener. This is going to give us F1 equals to Fs multiplied by 340 divided by 325, right? And then we can name this our equation 1. And then now let's come to our second scenario when the learner is moving towards the sound source, right? So again, we are going to have FL equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs. And then what is FL? We are told that when the learner is moving towards the sound source, FL equals to F2, right? And then F2 is F1 plus 37. So we're going to have F1 plus 37 equals to Fs, which is unknown, right? And then we know fully well that our V is 340 plus or minus the velocity of the listener. So what is the velocity of the listener? The velocity of the listener, it is said to be 25 meters per second, right? So we're going to have plus 25 meters per second divided by 340 minus or plus 0, right? Because the sound source is now stationary. So this will be equals to F1 plus 37 equals to Fs multiplied by 365 divided by 340, right? We can go ahead and make F1 the subject of the formula. We're gonna get F1 is equals to Fs multiplied by 365 divided by 340 minus 37, and then we can call this equation 2. So I want you to realize something. If we say equation 2 equals to equation 1, then we can solve for Fs, right? Which is what we want. And then equation 2 is equals to equation 1 because they're all giving us F1, right? So equation 2 is Fs multiplied by 365. This is 365. Divided by 340 minus 37, and it's supposed to be equals to equation 1. Equation 1, which is Fs multiplied by 340 divided by 325. So what we are going to do, we are going to make Fs the subject of the formula, right? So we're gonna have minus 37 equals to Fs multiplied by 340 divided by 325 minus Fs multiplied by 365 divided by 340. So if we take fs as the common factor in the right hand side, we're gonna get minus 37 is equals to fs multiplied by 340 divided by 325 minus 365 divided by 340. And then from here we can divide both sides by this expression, right? And we get fs. So we're gonna get fs is equals to minus 37 divided by the expression, which is 340 divided by 325 minus 365 divided by 340. And then if you put this in your calculator, you're supposed to get the value of fs. And when I punch that in my calculator, I'm getting 1351.57 hertz. So if you can look at this problem that we just did, the physics is really straightforward, right? We have a scenario when the sound source is the one moving, and the scenario where the listener is now moving. As soon as you set up your equations, now you're just left with solving the math. So let's do 6.3. 6.3 says calculate the wavelength of the sound observed by the stationary learner, right? So we know that frequency equals to speed divided by wavelength. If we make the wavelength the subject of the formula because it's what we want, right? We're gonna get wavelength equals to the speed divided by the frequency. And then what is the speed? Because we're talking about sound here in air, right? We are told that the speed is 340. And then what is the frequency? The frequency is what we just calculated, right? Which is 1351.57, which is equals to 0.252 meters. And then 6.4. And then 6.4 says write down one application of the phenomenon referred to in question 6.1 in the medical field. So that's the Doppler effect, right? And one of the applications is ultrasound. And then another application is measuring the heartbeat. So you can write measuring the heartbeat, right? But this is the stuff you can just Google and you find it. And then 6.5 says the spectral lines from a star are shifted towards the longer wavelength of the spectrum. Does this represent redshift or blue shift? So longer wavelength, that is red shift. If it's shorter wavelength, then that is blue shift. A learner in a car moving at a constant speed of 10 meters per second. So we have V equals to 10 meters per second along a straight horizontal road, records the frequency of sound emitted by a distant stationary source. So the source in this instance is stationary and the listener is the one in motion, right? The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. So we have our V new of 20 meters per second. So to say, the graph below, not drawn to scale, is obtained from the results. On the y-axis, you can see we have the recorded frequency, and then on the x-axis, we have the speed of the car. So let me sketch what is going on. So this question is saying that this sound source is stationary. What is moving away is the listener, right? On the first scenario, the listener is moving away at a velocity of 10 meters per second. And then on the second scenario, the sound source still stationary, but the listener is now moving away at a speed of 20 meters per second. The first question says state the Doppler effect. This is the apparent change in observed frequency as a result of the relative motion between a sound source and an observer. 6.2 says use the graph to answer the following question, and then 6.2, there we have it. 6.2.1, write down the frequency of the sound source emitted by the stationary source. So the equation we have for Doppler effect is that the frequency observed by the listener equals to V plus or minus VL divided by V plus or minus Vs multiplied by frequency emitted by source. So for us to find the frequency emitted by the sound source using this equation, we need the frequency observed by the listener to be equal to the frequency emitted by the sound source. For us to obtain that using this equation, we need a VL here, the velocity of the listener, to be equals to the velocity of the sound source, so that V and V can cancel out, and then at the end we have FL equals to Fs. As far as we know, the velocity of the sound source is 0, right? Because it's stationary. So we go to a graph and look at a point where the velocity of the listener or the car is 0, so that the frequency of the listener can be equal to the frequency of the sound source. And then if you look at the graph, there's a green point there I'm making. That is where we have 0 and the x-axis, and then on the y-axis we have the frequency which is equals to 700 hertz, right? So the frequency emitted by the stationary source in this situation is 700 hertz. Then the question, and then it goes on to say, give a reason for your answer. The reason of the answer is that there's no relative motion between source and listener. They all have a velocity. So velocity of listener equals to velocity of source equals to 0 meters per second. No relative motion between the two. So the Doppler effect cannot take place, or its effect is 0 in this instance. Let's move on to the next question. 6.2.2. In which direction is the car moving relative to the source? Choose from towards or away. Give a reason for the answer. Again, we have to stick to the graph we have. That's what the question requires of us. So if when the velocity is 0, the frequency observed is 700 hertz. When the velocity is 10 meters per second, the frequency observed is 779.1. So it seems like when the speed of the car is increasing, the frequency observed is going down. That only happens when a vehicle is moving away, right? Whether the sound source is moving away from the listener or the listener is moving away from the sound source. But then in this situation, we know very well that the sound source is stationary, so the listener is the one moving away. So here we'll write away, and then the reason for that is that the frequency observed is less than the frequency emitted, right? Yes. Let's move ahead. 6.2.3 it says calculate the speed of sound in air. Okay, so what we're going to do, we have the data for when the speed of the vehicle is 10 meters per second and when the speed of the vehicle is 20 meters per second. So we're going to pick one between the two, and then we're gonna use it to find the speed of the air. So again, the first thing to do is to jot down the given information, right? So now we know that the frequency of the source is 700 Hertz. So we're gonna write that down. The velocity of A is our unknown, right? And the velocity of the source is 0. So the velocity of the listener, now we have to pick one point between the two. It's either we start with 10 or we start with 20. So let's pick 10. So there we have it, 10 meters per second. So on our Doppler effect, we're going to have one missing variable, which is the speed of sound in air. And then from that is just solving the math. So let's go ahead and do that. We have FL equals to V plus or minus VL divided by V plus or minus Vs multiplied by the frequency of source, right? The frequency observed by the listener when the speed of the car is 10 meters per second is 679.1, which is equals to this V is what we're interested in, the speed of sound in M, and then the velocity of the listener, because the listener is moving away, we're supposed to have a minus on the numerator, right? If it was moving towards, then we're going to have a plus. So there we're going to have V minus 10 divided by the velocity of sound in air, and then the listener stationary, so we're going to have plus or minus 0 multiplied by frequency of source. Frequency of source is 700 Hertz, so we're just going to have that there. So if we write this nicely, we get 679.1 equals to V minus 10 divided by V multiplied by 700. If I divide both sides by 700, I will get 679.1 divided by 700 equals to V minus 10 divided by V. Cross multiply, I get 679.1 V equals to 700 V minus 700 multiplied by 10. Take this value here to the left hand side. I get 679.1 V minus 700 V equals to minus 7,000, right? Yeah, there we have it. So now I can take V as a common factor. That will give me 679.1 minus 700 equals to minus 7,000. And then V is thus equals to minus 7,000 divided by 679.1 minus 700. Let me put that in my calculator real quick. It's taking a bit longer than I expected. Just give me a sec. So we have minus 7,000 divided by 679.1 minus 700. That is 334.993 meters per second. So yeah, that is what I'm getting. So what I'll ask you guys to do is to use the other point when the velocity is 20 meters per second and see if you get the same thing. This is a series of videos. I've done question 5, 4, 3, 2 from this question paper. So if you click on the channel, you'll get all of that. Please leave a like, subscribe, and I'll see you next time. In this video, we're going to do 18 past exam questions based on Doppler effect. So if you look at the left hand side, we already have a question there. Question 7. So let's go ahead and start. The first thing I like to do, I like to read the problem statement and I jot down all the information that I think would come in handy that will help me solve the problem. So let's go ahead and do that. Dolphins use ultrasound to scan their environment. Interesting. When a dolphin is 100 meters from a rock, it emits sound waves of frequency 250 kilohertz, 250,000 hertz, while it's swimming at 20 meters per second towards the rock. Assume that the speed of sound in water is 1,500 meters per second. The first question says, calculate the frequency of the sound waves detected by a detector on the rock. So in this instance, the rock is the observer, is the listener, so to say. So the dolphin is 100 meters from a rock. That's not important in solving this problem we have here. And then frequency emitted by the source is 250 kilohertz, which is 250,000 hertz, right? Kilo is 1,000. While it's swimming at 20 meters per second, so we know that the velocity of the source is 20 meters per second towards the rock. So let's just put an arrow there to denote that is moving towards. Then V of sound on water is 1,500 meters per second. Then we're supposed to calculate the frequency of the sound source, the frequency of the sound waves detected by the detector on the rock. So we have F of listener is equals to F of source, V plus or minus V of listener divided by V plus or minus V of source. So we are interested in finding VL. We have everything else. So in this case, it's just a matter of subbing in what we have in the equation. So we're going to have frequency of source is 250,000 kilohertz multiplied by 1,500 the speed of sound in water, and then the listener is stationary, so you can have plus or minus 0, it wouldn't matter. And then on the denominator we have 1,500 for the speed of sound in water, and then the dolphin is moving toward. If it's moving towards, then we have minus on the denominator. If it was moving away, then we're going to have plus. So we're going to have 1,500 minus 20, which equals to, now it's just a matter of putting that into your calculator. 250,000 multiplied by 1,500 divided by 1,480, and then that's going to give us 253,378,3784 hertz, which you can convert to kilohertz, and then you're going to have 253,38 kilohertz. That's it for this question. Maybe one thing that will have thrown you off is the speed of sound in water. That is 1,500. Maybe you are used to the speed of sound in air, and then you sub in 340 or 343, something around that, and then you're completely wrong. Okay, let's move ahead. 7.2 says, when the dolphin is 50 meters from the rock, another ultrasound wave of 250 kilohertz is emitted. How will the frequency of the detected sound waves compare with the answer calculated in question 7.1? Write down only higher, lower, or remains the same. Explain your answer. The frequency detected. So what's the formula of the frequency detected? It's F of FL equals to Fs V plus or minus VL divided by V plus or minus Vs. What are the variables that affect the frequency detected? Is the frequency emitted, the velocity of the sound in that medium, the velocity of the listener, and the velocity of the sound source. The distance between the two has no effect as far as this formula is concerned. So now, because the distance between is no longer 100 meters and it's 50 meters, it won't matter. So the right answer is remains the same, right? Remains the same. And then it says explain your answer. You'd explain your answer by writing this formula and stating that the distance between the sound source and the observer is not a variable in the equation we use to determine the frequency detected. Let's go ahead and move to the second question. The first step again, read the statement that is given and write down any information that we feel would come in handy. So the siren of a police car produces a sound of frequency. So frequency of source 420 hertz. A man sitting next to the road notices that the pitch of the sound changes as the car moves towards and then moves away from him. 7.1. Rather, the name of the above phenomenon, we know this is Doppler effect because the frequency is changing because of relative movement between the sound source and the observer. 7.2. Assume that the speed of sound in air, so we have V equals to 340 meters per second. Calculate the frequency of the sound source of the sound of the siren observed by the man when the car is moving towards him. So V of source equals to 16 meters per second towards him. We just denote that by an arrow. So back again, we're going back to the formula. F of L equals to F of S V plus or minus VL divided by V plus or minus Vs. So what would you do? So maybe the right thing to do right now is pause the video and try it out by yourself and see if you will get the answer right. I'm assuming you paused the video and you tried it by yourself, and then now we can do it together. We're interested in finding the frequency observed. So that is FL. Frequency of source, we already wrote it down when we were reading our problem statement. That is 420 Hz multiplied by the sound of the speed of sound in air, which is given as 340 plus or minus 0. The observer is stationary. 340. Because it is moving towards, again, on the denominator, we have a minus. If it was moving away, then we'd have a plus. So that is minus 16. As the speed of the sound source is given, equals to. Now it's just a matter of putting it into the calculator. We have 420 multiplied by 340 plus or minus 0. So we don't have to put anything there. Then we have 340 minus 16, which is going to be 440.74 hertz. Yeah, that is it. 7.3, 7.3.1. The question says, the police car moves away from the man at constant velocity, then slows down and finally comes to a rest. How will the observed frequency compare with the original frequency of the siren when the police car moves away from the man at constant velocity? When it's moving away, the observed frequency is gonna be smaller than the original frequency, because we're going to, in the denominator, we're going to have a minus sign, and then on the denominator we're going to have a positive sign. So if you increase the denominator and then you keep the numerator the same, the number overall is going to be smaller. There's no need for an explanation. 7.3.2. So let's go back to the formula. We have f of L equals to f of S V plus or minus VL. Everything we say in every calculation we do, we're basing it in this formula and nothing else. So they're saying that the car is slowing down. So this VS is getting smaller, right? So if VS is getting smaller and then the numerator is the same, then FL will go up, because now we're dividing by smaller number. So the observed frequency will increase. It sounds very counterintuitive because the car is still moving away, but then if we base it on this formula, then it's supposed to increase. Let's move ahead. Another question 7. An ambulance with its siren on moves away at constant velocity from a person standing next to the road. The person measures a frequency which is 90% of the frequency of the sound emitted by the siren on the ambulance. Name the phenomenon observed. We already know this Doppler effect because the frequencies observed is different from the frequency emitted due to relative movement between the sound source and the observer. 7.2. If the speed of sound in air is 340 meters per second, calculate the speed of the ambulance. So one thing that can throw you off in this situation is the fact that we're not given the frequencies per se. We're given that now the observed is 90% of the emitted. So because the observed is less than the emitted, then we know the vehicle is moving away, right? So we have FL equals to FS V plus or minus VL divided by V plus or minus VS. FL, that which is observed, is equals to 90 FS, right? Then FS is just FS, it's itself 90% FS, not 90 FS. And then V is just the speed of sound in, I'm very sorry for that. V is just the speed of sound in air, and then VL is 0, the observer is stationary, and then VS is our unknown. So let's go ahead and put that into the equation. So FL is 90% of FS, right? So that's just 0.9 FS, which equals to FS itself. Then we have multiplied by 340. The observer is stationary, plus or minus 0. 340 again, and then it's moving away. So if it's moving away, we're supposed to have plus on the denominator. If it was moving towards, then we're going to have minus on the denominator. So plus VS. What I'm going to do, I'm going to divide both sides by FS, right? So if you divide, so if you divide the right hand side by FS, FS and FS are going to cancel out, and then on the left hand side, if you divide 0.9 FS by FS, you're just going to be left with 0.9. So we have 0.9 equals to 340 divided by 340 plus VS. So now let's cross multiply. We have 0.9 multiplied by 340 plus 0.9 VS equals to 340 multiplied by 1. Let's take this, what we have here, to the right hand side. So we're gonna have 0.9 VS equals to 340 divided by 0.9 multiplied by 340. Now we divide both sides by 0.9, so we're going to have VS equals to 340 divided by 0.9 multiplied by 340 divided by 0.9 equals to now it's just a matter of putting that in the calculator. Let me go ahead and do that. So we have 340 divided by 0.9 multiplied by 340 divided by 0.9. 40 divided by 0.9 so Vs is 1.2345 meters per second. This answer seems very fishy. It's so small. I don't know if I did something wrong, but yeah, let me just move on. Question 6. We're going to read the problem statement again, like we always do. The siren of a burglar alarm system has a frequency of source. I'm assuming frequency of source equals to 960 Hz. During a patrol, a security officer traveling in his car hears the siren of the alarm of a house and approaches the house at a constant velocity. A detector in his car registers the frequency of the sound as 1000 Hz. So frequency observed is 1000 Hz. Name the phenomenon, blah 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 blah. We know that that's the Doppler effect because the frequency is changing due to a relative what? It's changing due to relative movement between the sound source and the observer. 6.2. Calculate the speed at which the patrol car approaches the house. Use the speed of sound in S. Back to the basics. FL equals to FS V plus or minus VL divided by V plus or minus VS. FL is 1000, we're given that. FS is 960 Hz, we're given that. And then V is 340. It says we're supposed to calculate the speed at which the car is approaching. So now is the velocity of the observer that we're supposed to calculate. If it's approaching, then on the numerator we have a plus, right? Plus VL. If it was moving away, then we'd have minus. Yeah. On the denominator we have 340. The sound source is stationary, so plus or minus 0 doesn't matter. So that is 1000 equals to 960 multiplied by 340 plus VL divided by 340. I'm going to divide both sides by 960, so we're going to have 1000 divided by 960 equals to 340 plus VL divided by 340. We're going to cross multiply, so we're going to have 340,000 equals to 960 multiplied by 340 plus 960 multiplied by VL. I'm going to take this which we have here to the left hand side so that I can isolate VL. So we're going to have 340,000 minus 960 multiplied by 340 equals to 960 VL. I'll divide both sides by VL, so we're gonna end up with VL equals to, let me put that into my calculator, 340,000 minus 960 multiplied by 340 multiplied by 340 divided by 960. So that is 14,1667 meters per second. Yeah, we stick to the basics again. We write down the information we have, we sub in, and then we solve for the variable. Let's move ahead. 6.3. If the patrol car had approached the house at a higher speed, how would the detected frequency have compared to the first observed frequency of 1000 Hz? every question we have, we stick to the formula. So let's go ahead and do that. FL equals to FS V plus or minus VS VL, I meant, divided by V plus or minus VS. So it's saying the car is now approaching at a higher speed. So we're increasing this number here. So we're increasing the numerator and keeping the denominator the same. So if you increase the numerator and keep the denominator the same, then the overall number will be higher, right? So in this instance, the frequency will be higher than. To prove that, if you have 1 over 2, then this is 1 over 2. But then if you increase the denominator to 4, if you increase the numerator to 4, then let's say you have 4, and then you keep the denominator the same, then now you have 2, and then 2 is greater than 1 over 2. So every time you increase the numerator and you keep the denominator the same, the number overall will go up. Let's move ahead. Question 6. The whistle of a train emits sound waves of frequency 2000 Hz. So F of sound source 2000 Hz. A stationary listener measures the frequency of these emitted sound waves at frequency of listener 2080 Hz. So we can see that the frequency observed is greater than the frequency emitted. So it's either the sound source is moving towards the listener or the listener is moving towards the sound source. Name the phenomenon responsible for the observed change in frequency. That's Doppler effect. The frequency observed is different from the frequency emitted because of the relative change in position between observer and listener. 6.2 is the train moving away from or towards. It's moving towards, right? It's moving towards because the observed sound is greater than the emitted. 6.3, calculate the speed of the train. F of L equals to F of S. Sticking to the basics again, the formula we use, VL divided by V plus or minus VS. The observed frequency is 2080 Hz equals to 2000 Hz. Speed of sound in air 340. It says the speed of the train. Okay, so plus or minus 0 here. The listener is stationary. 340 minus VS. It's minus in the denominator if the sound source is moving towards. If the sound source was moving away, then we were going to have plus on the denominator. So let's go ahead and do that. Divide both sides by 2000, right? So it's 2080 divided by 2000 equals to 340 divided by 340 minus VS. We're going to cross multiply. So we're going to have 2000 multiplied by 340 equals to 2080 multiplied by 340 minus 2080 VS. So I'm going to take this expression here to the left hand side so that I can isolate VS. So we're going to have 2000 multiplied by 340 minus 2080 multiplied by 340 equals to minus 2080 multiplied by VS. And then now I'm going to divide both sides by VS and see what we get. So let me go ahead and put that into my calculator. So we're going to have VS equals to okay, let's see what we have. 2000 multiplied by 340 minus 2080 multiplied by 340 divided by minus 2080. That gives me 13.0769 meter per second. I think that's around about it. speed of the train. 6.4 says, which will the frequency observed by a passenger sitting on the train be greater than, equal than, or smaller than 2000 Hz? Explain the answer. Will the frequency observed by a passenger? Oh, okay, the passenger is in the train. So if the passenger is in the train, okay, yeah, interesting question. 6.4, let's stick to the formula again like we always do. FL equals to Fs V plus or minus VL divided by V plus or minus Vs. This Fs is remaining the same. V is the same. V is the same. So now, because we're talking about the passenger in the train, V passenger is the same as Vs. So basically what we have on the numerator is equals to what we have on the denominator. So this is just gonna cancel out, right? And then we're just gonna be left with FL equals to Fs. So the answer here would be equal to. Why are we saying equal to? We're not taking a guess. We're not just saying it because we have to choose one of the options. We're basing it on the formula. Each and every question you come across, you're going to be basing it in this formula. That's it for this question. Let's move to the next one. Question 6 again. A lot of question 6, it seems. A train approaches a station at a constant speed. So V of source, I'm assuming it's source, I can always change. With its whistle blowing at a frequency, okay, frequency of source 458 Hz. Standing on the platform, he has a change in pitch as the train approaches him. Oh, okay, somebody approaches him, passes him, and moves away from him. Okay, 6.1, name the phenomenon that explains the change in pitch had by the observer. Change in pitch had by the observer, that's Doppler effect. The pitch is changing because of relative movement between the observer and the sound source. 6.2, calculate the frequency of the sound that the observer hears while the train is approaching him. Use the speed of sound in airs, 340 Hz. Calculate the frequency. Okay, so we are looking for FL, which is equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs, like we always have. The emitted frequency is 458 Hz, right? Speed of sound in air we given as 340. The observer is stationary plus or minus 0 divided by speed of sound in air 340. The train approaches, so it's moving towards, then we subtract Vs, which is 20. If it was moving away, then we're going to add. Then that's it. We just plug that into the calculator. So let me go ahead and do that. 458 multiplied by 340 divided by 340 minus 20, 320. That is 486,625 Hz. 6.3. How will the observed frequency change as the train passes and moves away? From the observer, write down all the increase. It's going to decrease. It's going to decrease. Why are we saying it's going to decrease? Let's go back to the formula. FL equals to Fs V plus or minus VL divided by V plus or minus Vs. Because when it's moving towards, on the denominator we have a subtraction of Vs, right? So if you keep the numerator the same and you decrease the denominator, the number goes up. So when it's approaching, FL goes up. When it's moving away, we have an addition on the denominator. So you keeping the numerator the same and you increasing the denominator, the overall number goes down. 6.4. how will the frequency observed by the train compare to that of the sound waves emitted by the whistle, by the train driver? The train driver and the whistle are traveling at the same speed, so we're going to have Vs equals to VL. If we put that into the equation, we get VL equals to Fs V, let's say plus or minus VL divided by V plus or minus VL again, because Vs is the same as VL. So in this case, the numerator and the denominator are going to cancel out, and we're going to have FL equals to Fs. So for 6.4, it will be equal to. Let's move ahead and do questions that are a bit different from what we're doing, that involve graphs and so on. So on the left hand side, we have a question here, question 6. We're going to start by reading the problem statement like we always do. A bird flies directly towards the stationary bird watcher at constant velocity. The bird constantly emits sound waves at a frequency of 1650 Hz. So from that, we already know that the frequency emitted by the source is 1650 Hz. The bird watcher hears a change in pitch as the bird comes closer to him. So the bird is moving closer to the observer. And then 6.1 says, write down the property of sound that is related to pitch. By definition, Doppler effect is the change in frequency, wavelength, or pitch because of relative movement between an observer and a sound source. So a property that is related to pitch is frequency, right? But at the same time, frequency is related to wavelength. So we're going to write wavelength slash frequency like I just did. 6.2, give a reason why the bird watcher observes a change in pitch as the bird approaches him. This is because of the Doppler effect, right? When the bird watcher, when the bird is moving towards the bird watcher, the waves are compressed, so the wavelength goes down and the frequency goes up. So that's why there will be a change in pitch when the bird approaches the bird watcher. Let's go ahead. 6.3. We have a graph, pressure versus distance in meters. The first question says, from the graph, write down the wavelength of the detected waves. Again, we go back to definitions. What's a wavelength? A wavelength is the distance between two crests, right? So if we have this crest here and then we have this crest here, this line joining the two is our wavelength. So if we have this line here cutting the axis and we have this line cutting the axis, the distance between these two is the wavelength. So you can see there from the graph that we have 0.3 minus 0.1, which will give us 0.2 meters. If we use the other point, if we use the crest instead, between 0.3 and 0.2, we have 0.25 minus between 0 and 0.1, we have 0.05, which will also give you 0.2 meters. So the wavelength, we calculated it by just taking to the definition of what a wavelength is. 6.4.1, the first question says frequency of the waves detected by the bird watcher. So we know from definition that frequency is given by the speed of the certain wave in a certain medium divided by wavelength. We've already determined what the wavelength is. It's 0.2 meters. And then on the question, we're given that the speed of sound in air is 350 meters per second. So we're just going to plug that into the equation. We're going to have 340 meters per second divided by 0.2 meters. 0.2 meters. So let me go ahead and put that in the calculator. We're going to have 340 divided by 0.2, which is going to give us 1700. The SI unit of frequency is hertz, which makes sense. The emitted frequency is 1650 hertz, right? And the bed is moving towards the bed watcher, so we anticipating a frequency that is greater than that which is emitted, and then that is true because, as you'd see, 1700 is greater than 1650 hertz. Moving to the next question, 6.4.2. It says magnitude of the velocity at which the bird flies. We have frequency, we have the speed of sound in air, we have the wavelength is. So the formula we're going to use, the Doppler Effect formula, right? Which is given by the frequency of the listener observes equals to the frequency of the source multiplied by the velocity plus or minus VL divided by V plus or minus VS. The frequency observed by the listener is 1700. We calculated in 6.4.1. So we're just going to go ahead and put that on. So that will give us 1700 equals to 1650, which is the frequency emitted by the sound source, right? V is 340, is given on the question. The listener is stationary, so we're going to have plus or minus 0. The sign won't matter in this case. And then 340 again, because the sound source is moving towards the observer. In the denominator, we're supposed to have minus. If it was moving away, then we're going to have plus. So we're going to have minus V of sound source, which is our unknown. So what I'm going to do here, I'm going to divide both sides by 1650. So let me just go ahead and do that. So we're going to have 1700 divided by 1650 equals to, in the right hand side, they're going to cancel out, so we're just going to be left with 340 plus or minus 0, which will just give us 340 divided by 340 minus VS. Now what I'm going to do, I'm going to cross multiply. So I'm going to have 1700 multiplied by 340 minus 1700 multiplied by VS, which is equals to 1650 multiplied by 340. I'm going to take this expression to the right hand side so that I can try and further isolate VS. So I'm going to have 1700 VS equals to 1650 multiplied by 340 divided by 1700. I'm moving a step forward. I'm still supposed to take that expression to the right hand side. So let me do that. It's going to be minus 1700 multiplied by 340. So after I've done that, I can then divide both sides by minus 1700, which is here. So let me just write that down for clarity. 1700 cancel out. So we're going to have VS equals to 1650 multiplied by 340 minus 1700 multiplied by 340. Everything divided by minus 1700. So that's it for this question. I'm just going to plug that into the calculator. 1650 multiplied by 340 minus 1700 multiplied by 340. Everything divided by minus 1700. And that gives me 10 meters per second. It seems too good of an answer, but I can't notice anything I did wrong, so I'm assuming it's right. Let me scroll down and look for a question that has a graph in it so that we can do a question that's a bit different. Okay, we have a table there, so let's just do this question. So question 6, 6.1, start by reading the problem statement like we always do. The data below was obtained during an investigation into the relationship between the different velocities of a moving sound source and the frequencies detected by a stationary listener. For each velocity, the effect of wind was ignored in this investigation. The first question says, write down the dependent variable for this investigation. Here on the problem statement, it says the relationship between different velocity and the frequencies detected. So we are differing the velocities and we figuring out what the detected frequency is. So the dependent variable is the frequencies, and then the independent is what we are switching around, which is the velocity, right? So dependent variable is the frequencies detected. If it was looking for independent variable, it will be the velocities of the sound source. 6.1.2 state the Doppler effect in words as the change in frequency, pitch, wavelength of a frequency observed by a listener because of relative movement between a sound source and the listener. 6.1.3, was the sound source moving towards or away from the listener? Give a reason for your answer. Okay, let's stick to the equation, right? FL equals to Fs multiplied by V plus or minus VL divided by V plus or minus Vs. If you look at the denominator here, we have Vs, right? Plus or minus Vs. If the sound source is moving away, we have a plus on the denominator. If you have a plus on the denominator, this whole number will go down. So the frequency observed will be going down. If it's moving towards, you will have a minus on the denominator. So the whole number will go up. So in our case, the frequency is going down. We start with 900, we have 8745, we have 850, we have 897. So it means we have a plus here on the denominator, and we only have a plus on the denominator when the sound source is moving away. So here we're going to have away from, because we're supposed to write towards or away from, and then give a reason for the answer. The reason is that the frequencies observed by the listener is decreasing, right? So it only makes sense that it is moving away. So 6.1.4 says use the information in the table to calculate the speed of sound during the investigation, right? I think the trick of the question here, I think, is to realize that for experiment 1, Fs equals to Fl, right? So to elaborate on that, we know that Fl equals to Fs V plus or minus Vl divided by V plus or minus Vs, right? In experiment 1, the velocity of the source is 0. The listener is stationary, so the velocity of the listener is equals to 0. If we put that into the equation, we're going to have Fl equals to Fs V plus or minus Vl divided by V plus or minus Vs. But Vs and Vl are 0, so we're going to end up with Fl equals to Fs multiplied by V plus or minus 0 divided by V plus or minus 0. This and this just cancel out, so Fl equals to Fs, right? So the frequency emitted by the sound source is basically 900 Hz if you look at experiment 1 and pay attention to details. So to calculate the speed of sound during the investigation, we'll pick any of the other remaining experiments. So let's pick experiment 3 because it has like 20 and 850. 850 is better to work with compared to 874. So FS, we deduce that is 900 hertz, right? And then FL for the third experiment is 850 hertz. VS is 20 meters per second. We're given that. And then we sub VL equals to 0. V is our unknown. So let's plug that into the equation. 850 equals to 900 multiplied by V plus or minus 0 divided by V minus 20. Plus 20, I meant. We plus in because the source is moving away. If the source was moving towards, then we're going to have a subtraction on the denominator. So let's divide both sides by 900. We're going to get 850 divided by 900 equals to V divided by V plus 20, right? Let's go ahead and multiply. We're going to get 850 V plus 850 multiplied by 20, which will give us 900 multiplied by V. Let's take the 850 V to the other side. We're going to get 850 multiplied by 20 equals to 900 V minus 850 V, which will just be 50 V. So we're gonna get 850 multiplied by 20 equals to 50 V. Divide both sides by 50. This would imply that V equals to 850 multiplied by 20 divided by 50. Let me plug that into my calculator. That will give us 340 meters per second, which is something you'd expect. You'd expect an answer around 340. Yeah, that's it for that question. Let's move ahead. 6.2. The spectral lines of a distant star are shifted towards the longer wavelengths of light. Is the star moving towards or away from the Earth? It's moving away from the Earth. It is shifted towards the longer wavelengths, then is shifted towards the red end of the spectrum. It's a red shift, and the red shift occurs when a star is moving away from the Earth.